Superclusters are among the largest known structures in the observable universe. The Virgo supercluster, also known as the local supercluster, is 110 million light-years in diameter. It contains 4,000 luminous galaxies, organized into 100 galaxy groups and galaxy clusters. The Virgo supercluster's volume is approximately 7,000 times larger than our local group and 100 billion times larger than the Milky Way. For the first time, we are at a distance where we can see the galaxies are not just evenly distributed throughout space. In this picture, each galaxy is a point of light. And these points are crowded together into galaxy clusters. And these clusters are crowded together into galaxy clouds. And these clouds of galaxy clusters are grouped up into the supercluster. Let's take a look at some of the galaxies in the Virgo supercluster. This image of the barred spiral galaxy, NGC 4314, shows the entire galaxy, including the bar of stars bisecting the core and the outer spiral arms, which begin near the ends of the bar. That's normal enough. But this Hubble image reveals clusters of infant stars that formed in a ring around the core. This close-up view by Hubble also shows other interesting details in the galaxy's core. Dust lanes, a smaller bar of stars, dust and gas embedded in the stellar ring, and an extra pair of spiral arms packed with young stars. These details make the center resemble a miniature version of the spiral galaxy itself. This is a unique view of a galaxy tilted edge-on to our line of sight. The image highlights the galaxy structure, a subtle reddish bulge surrounding a bright nucleus, a blue disk of stars running parallel to the dust lanes, and a transparent outer halo. The dust lane is slightly warped compared to the disk of stars. This warp indicates that NGC 5866 may have undergone a gravitational tidal disturbance in the distant past by a close encounter with another galaxy. Hubble snapped a view of what may be the youngest galaxy ever seen. Zwicky 18 may be as young as 500 million years old. The galaxy is classified as a dwarf irregular. This galaxy is typical of the kinds of galaxies that inhabited the early universe. Hubble reveals a majestic disk of stars and dust lanes in this view of the spiral galaxy NGC 2841. A bright cusp of starlight marks the galaxy center. Spiraling outward are dust lanes that are silhouetted against the population of whitish middle-aged stars. Much younger blue stars trace the spiral arms. Notably missing are pinkish emission nebula, indicative of new star birth. It is likely that the radiation and supersonic winds from fiery, superhot young blue stars cleared out the remaining gas and hence shut down further star formation in the regions in which they were born. This picture shows a bubble in the center of a galaxy's disk. The structure is more than 3,000 light-years wide and rises 3,500 light-years above the galaxy's disk. This is a close-up view of the bubble. Gaseous filaments at the top of the bubble are whirling around in a vortex and are being propelled into space. Eventually, this gas will rain down upon the galaxy's disk, where it may collide with gas clouds, compress them, and form new generations of stars. Messier 100 is a perfect example of a grand design spiral galaxy. A type of galaxy with prominent and very well-defined spiral arms. These dusty structures swirl around the galaxy's nucleus and are marked by a flurry of star formation activity that dots M100 with bright blue, high-mass stars. Messier 77 is a spiral galaxy containing a supermassive black hole. The X-ray images and spectra obtained using Chandra show that a strong wind is being driven away from the center of the galaxy at a rate of about 1,000,000 miles per hour. This wind is likely generated as surrounding gas is accelerated and heated as it swirls towards the black hole. A portion of the gas is pulled into the black hole, but some of it is blown away. High-energy X-rays produced by the gas near the black hole heat the outflowing gas, causing it to glow at lower X-ray energies. These results help explain how an average-sized supermassive black hole can alter the evolution of the entire host galaxy. One of the ways we constructed the form of our home Milky Way galaxy is to examine galaxies that are similar in shape and structure. Spiral galaxies like NGC 3949, pictured in this Hubble image, fit the bill. Like our Milky Way, this galaxy has a bluish disk of young stars peppered with bright pink star birth regions. In contrast to the blue disk, the bright central bulge is made up of mostly older, redder stars. Most galaxies form new stars at a fairly slow rate, but members of a rare class known as starburst galaxies blaze with extremely active star formation. NGC 3310 is forming clusters of new stars at a prodigious rate. There are several hundred star clusters visible in this image as the bright blue diffuse objects that trace the galaxy's spiral arms. Each of these star clusters represents the formation of up to about 1,000,000 stars. NGC 4013 is another spiral galaxy similar to our own Milky Way. This Hubble picture reveals, with exquisite detail, huge clouds of dust and gas extending along as well as far above the galaxy's main disk. Even at 55 million light-years, the galaxy is larger than Hubble's field of view, and the image shows only a little more than half of the object. NGC 4522 is a spectacular example of a spiral galaxy that is currently being stripped of its gas content by its strong central winds. A number of newly formed star clusters that developed in the stripped gas can be seen in the Hubble image. The picture highlights the dramatic state of the galaxy with an especially vivid view of the ghostly gas being forced out of the center. Bright blue pockets of new star formation can be seen to the right and to the left of center. Here we are zooming into NGC 4710 in the Virgo cluster. This magnificent giant galaxy is tilted edge-on to our view from Earth. This perspective allows astronomers to easily distinguish the central bulge of stars from its pancake-flat disk of stars, dust, and gas. When staring directly at the center of the galaxy, one can detect a faint, ethereal X-shaped structure. Such a feature, which astronomers call a boxy or peanut-shaped bulge, is due to the vertical motions of the stars in the galaxy's bar and is only evident when a galaxy is seen edge-on. In 1995, the majestic spiral galaxy NGC 4414 was imaged by Hubble as part of the Key project on extragalactic distance scales. An international team observed this galaxy on 13 different occasions over the course of 2 months. Based on their discovery and careful brightness measurements of Cepheid variable stars, the Key project astronomers were able to make an accurate determination of the distance to the galaxy, 62 million light-years. This takes us to the final rung in our distance ladder, redshift and Hubble's law. In 1923, after finding the V1 Cepheid in Andromeda and determining that Andromeda was an entire galaxy over 1 million light-years from our own, he turned his sights on other spiral and elliptical nebula and found that they were galaxies as well. In his studies of these galaxies, he measured their radial velocity as determined by the shift in spectral lines, as we discussed in our segment on planetary nebulae. He found that except for a few nearby galaxies, all the spectral shifts were to the red. They were all moving away from us. Using galaxies in our local volume, he found what we see here with galaxies in the Virgo supercluster. Simply stated, the further away a galaxy is, the greater the redshift, and therefore the faster it is receding away from us. The relationship is linear, a straight line. So the equation is simple. The receding velocity of a galaxy is equal to its distance times a constant now known as the Hubble constant. This constant has been refined over time, and the distances used to see how far out it holds has increased by orders of magnitude. With our modern ability to determine distances with space telescopes like Hubble analyzing Type 1a supernova out to billions of light years. The gray box at the lower left shows the region that Hubble probed. The current best value for the Hubble constant is 13.6 miles per second per million light years. That is, the receding velocity of a galaxy goes up by 13.6 miles per second for each additional million light years away from us that it is. From a distance ladder point of view, now that we have the Hubble constant and we can measure redshift, we can calculate distance. NGC 1427A is plunging headlong into the Fornax cluster at nearly 400 miles per second. This galaxy will not survive long as an identifiable galaxy passing through the cluster. Though the universe is full of spiral galaxies, no two look exactly the same. NGC 3982 is striking for its rich tapestry of star birth, along with its winding arms. The arms are lined with pink star-forming regions of glowing hydrogen, newborn blue star clusters, and obscuring dust lanes that provide the new material for future generations of stars. The Hubble telescope captured a display of starlight, glowing gas, and silhouetted dark clouds of interstellar dust in this image of the barred spiral galaxy NGC 1300, a prototypical barred spiral galaxy. NGC 5584 contains Cepheid variables and one recent Type 1a supernova. As you know, we use these two standard candles as reliable distance markers to measure the universe's expansion rate. 5584 was one of the 8 galaxies astronomers studied to measure this rate. In total, the project analyzed more than 600 Cepheid variables, including 250 in 5584. NGC 1316 is one of the brightest ellipticals in the Fornax galaxy cluster. This Hubble image shows NGC 4639, a spiral galaxy located 78 million light-years away in the Virgo star cluster. The blue dots in the galaxy's outlying regions indicate the presence of young stars. Among them are older, bright Cepheid stars. After using Cepheids to calculate the distance to 4639, the team compared the results to the peak brightness measurements of supernova 1990N, a Type 1a supernova located in the galaxy. Once again, Type 1a supernova were found to be reliable standard candles. This Hubble image shows the inner region of galaxy NGC 4319. The unusually dark, misshapen dust lanes in the galaxy's inner region are evidence of a disturbance probably caused by an early interaction with another galaxy. This galaxy was one of several hosts of recent Type 1a supernova observed by astronomers to refine the Hubble constant. In the 1930s, Edwin Hubble made precise measurements of Cepheid variable stars in this galaxy, highlighted by green circles in the 4 inset boxes. These Cepheids are used to calculate the supernova that was observed in the galaxy in 1995. In 1994, NGC 3370 hosted a Type 1a supernova designated SN 1994AE. This stellar outburst briefly outshone all of the tens of billions of other stars in its galaxy. Although supernovae are common, with one exploding every few seconds somewhere in the universe, this one was special. This supernova was one of the nearest and best observed since the advent of modern digital detectors. NGC 1309 is one of about 200 galaxies that make up the Eridanus galactic group. It was home to Type 1a supernova SN 200FK. Its light reached Earth in September 2002. It also contains a number of Cepheid variables resolved by the Hubble Space Telescope. And, once again, the Type 1a was shown to be an excellent standard candle. NGC 7049 is the brightest of a cluster of galaxies called Brightest Cluster Galaxies, or BCG for short. Typical BCGs are some of the oldest and most massive galaxies. Direct measurements, triangulation, and parallax took us across Earth, the solar system, and nearby stars. We added expansion parallax for planetary nebula and a number of powerful standard candles that were verified against stars that could be measured via parallax. This took us all the way across the Milky Way and into our local supercluster, the Virgo supercluster. Here, Cepheid variables confirmed the accuracy of Type 1a supernova as an excellent standard candle. This is critical because even with the Hubble Space Telescope, we can't see Cepheid stars much further than 100 million light-years. But we can see Type 1a supernova out to 8 billion light-years. In addition, Cepheids in Type 1a's have given us redshift as a way to tell distance. This rung is only limited by what is visible, and we'll see in later segments we can see out to around 13 billion light-years. The Hubble constant is not only critical for determining distance via redshift, it showed that the universe was expanding with time. This in turn implied that going backwards in time, everything was getting closer. This leads directly to the Big Bang theory. But we'll go into that later in our segment on the cosmos. Here we have just seen a few of the galaxies in the vast Virgo supercluster. But Virgo is only one of millions of superclusters in the observable universe. In the next segment, we'll take a look at our local group of superclusters.